I'm going to walk you through step by step how to write down half equation. But before we even start that, we really need to get confident in understanding what happened in terms of movement of electrons in a chemical reaction. That's why I've set up this little table that always helps analyzing a chemical reaction when we talk about redox. Well, first of all, redox, it's a reaction where both reduction and oxidation take place. And oil rig is really the little thing we needed to remember, the little acronym that means oxidation is loss of electrons, reduction is gained of electrons. Keeping that in mind, it will help us understanding what's reduced and what's oxidized. So at the very beginning of this topic, because it seems really, really complicated to do all of this reasoning plus understanding the charges and the movement of electrons is always a bit counterintuitive. It's important to get used to this mental process, I would say. Then it would get faster and faster. You won't need to do the table, but just at the start, I think this is the way to fully analyze a chemical reaction. So let's take an example. An example of redox could be, let's take this magnesium reacting with hydrochloric acid to form magnesium chloride and hydrogen gas. We can balance it, of course, first, and now we need to think about, okay, is this a redox reaction? If it is, what has been reduced, what has been oxidized? Well, the first thing is looking at one element at a time, because when we talk about transfer of electron, that's the way, one element at a time. So elements, we have magnesium, we have hydrogen, and we have chlorine. Magnesium. How does it start as a reactant? What charge does it have? Well, it's an element on its own. If it's so, the charge is going to be zero. Always think it as has lost or gained electrons. Well, no, because there's nothing in that Mg that has lost or gained electrons. So the charge of an element is always zero. Hydrogen, as a reactant, it's bonded to chlorine, and we know that hydrogen always has a charge of +1. So it's bonded, that's why it has a charge. Chlorine is bonded to hydrogen, so it has a charge of -1. If you're not sure, periodic table, most of the time it tells us correctly the charge. Of course, the charge is only if the element is actually in a compound. So magnesium element, charge of 0. What happens as a product? Now magnesium is bonded to chlorine. So if it's bonded to chlorine, we need to remember ionic bond, transfer of electrons. So what's the charge of magnesium? If you can't work it out from the compound there, just look at the periodic table and the group number will help us predicting the charge. But we know that this has a charge because it's bonded to something else. So it would have a charge of +2. Chlorine, it's bonded to magnesium, a part that we can work out the charge from the compound, and we know magnesium, but from the periodic table, we know that chlorine is -1, and it's still going to be -1. Hydrogen, before it was bonded to chlorine, so had a charge of +1, but then it's gone to H2. This, I know it seems like it's bonded, because it's a covalent bond, but remember that some elements exist as diatomic molecules, so it's hydrogen bonded to itself, so that's the element. That's how we always write it as an element. And as we said, elements have not gained or lost any electrons, so the charge of that would also be 0. And now it's when we try to understand the movement of electrons. Magnesium has gone from a charge of 0 to a +2. We carefully need to think about what that means in terms of movement of electron. 0 to +2. It's less negative, lost electrons. Less negative, lost electrons. In fact, magnesium has lost 2 electrons, and that suggests you to really put a bit of brain effort here until it really clicks of how gaining and losing electrons affects a charge, because it is counterintuitive. Electrons are negatively charged. So if we look at hydrogen, we go from a charge of +1 to 0. So what does that mean? Well, +1, it goes up to less positive because it's 0, less positive. It means that he has gained electrons. In this case, he has gained 1 electron. Chlorine, nothing. so it doesn't matter. Reduce or oxidize? Oxidation is loss. Magnesium has lost electrons, so it's oxidized. Reduction is gain. Hydrogen has gained electrons, so it's been reduced. We can explain all of this in a little equation. This is called half equation. And half equations, they are useful to show the movement of electrons relative to just one atom only. Okay, so magnesium, that's right here, half equation. Magnesium starts, so that's only how we start a half equation. What's the starting element or ion? Magnesium, it's present just like that as an element. How does it finish? As we said, a charge of 2+. Remember, focus on one element at the time. And now you can think, okay, what has it done in terms of electron? It's oxidized, it has lost electrons. If electrons are lost, taken away from something, they're a product. That's why we would write it on the right-hand side, 2 electrons. Hydrogen, how does it start? It starts as a +1. How does it end? As an H2, the element. First thing, we need to balance the element because, of course, that's always what we do in equations. And then we think, what has happened? It has gained electron. Gain, come together, things that react together, it would be in the reactant, reduced in the reactant. And specifically, how many? Well, each hydrogen gained 1. So if we have 2 of them, it would be 2 electrons in total. I know it seems a super long explanation, but I would like you to really get trained to get this line of logic thinking, because then it will become a lot faster. But this is really all the information you need to be able to write half equations. So now I will put up another example. This table, again, it's really useful to help us at the start. And then, of course, we can just predict the charges a bit quicker and understand what that means in terms of gain or loss of electrons. And I will do another example. So this one was a reaction with a metal and acid. Another common one are displacement reactions of halogens. So let's get example: fluorine reacting with 2KCl, and it will form Cl2 plus 2Kf. A bit on the way. I put this don't know where to put the camera. Okay, right here. Hope it's not on the way. Okay, now stop this and try. So this is the complete table for this reaction. Let's take a bit slower constructing the half equations because that can be a bit confusing. Okay, so we need to think about this as an equation, right? So half equation, sorry, it's moving around. So half equation just tell us the movement of electrons, specifically from like focusing on one element only. So to construct the half equation without adding electrons, I would suggest you to start in one way, as like this, what we did here. So as a reactant, our element, how does it exist? So what is the element before? It's F2. What is the element after? It's 2 F, but with the K. But we don't care about the K, because as we said, half equation, the focus is on one element at the time. So we get rid of K, but what did we say about this fluorine? That it has a charge of -1. So we would write it as F -1. Notice the balancing is still there. And now we need to just show in this half equation what we said here, that has been reduced, that it's gained electrons. So gaining electrons come together, right? Something gain, come together. We have to write them down on the left-hand side of the equations. And in this transfer, that has been 2 electrons because each fluorine gains 1. So we either look as how many electrons have been transferred, or another thing. This we can get it from the equation and from this analysis of the element before, the element after. Before, in this case, was an element, F2, and after was present as an ion because it was bonded to potassium. And we don't care about the other elements. We just keep the potassium. And now we can think about, okay, where do I add electrons? As a reactant or as a product? Notice that on the right-hand side, we have 2F minus. So the total charge would be 2 minus, right? Because we have 2 of this negative ion. But here we have an element that is neutral. It doesn't have a charge, but we want to balance them out overall. So what we can do is add electrons on the opposite side. And by doing that, this also becomes -2, balancing out the charges. So the half equation can be done by, in this way, balancing charges or just carefully thinking about the movement of electrons. So let's do the second half equation for this. Again, the same thought. What has been oxidized or reduced? Well, we did the reduced, so let's look at the oxidized. It's chlorine. How does chlorine exist as a reactant? We said here it has a charge of -1. So it's chlorine -1. How does it exist as a product? We look at their product is charge of 0, so as an element, Cl2. We need to balance it like it's balanced in the overall equation, and now we need to think lost electrons, break apart as a product. Therefore, we would write it on the right-hand side, plus 2 electrons. Alternatively, look at the overall charges of each side of the equation. On the left-hand side, we have 2 chloride ions, so overall the charge on that side would be 2 minus. But here it's chlorine as an element, so it doesn't have a charge as we worked out before, but we need to make them even. We can only add electrons, so we add the 2 of them on this side to make this also -2. So make sure you understand fully and find the way that it's best for you to do a half equation. But I think the best way is always to start with what you have for sure, which is the elements on either side and the charges, how they change element to an ion or ion to element or changes in charges. And then you can try to think about what was the movement of electrons. If you don't understand the charges and can't work out where to add electrons, if on the left or on the right, just think that reduction is gain of electron, so they go on the left-hand side of the equation. Oxidation, loss of electrons, and they are added on the right-hand side of the equation. But I never approve memory, and I'd rather you really, really carefully understand it and work it out step by step. That's why I'm here, recorded, and you can listen as many times as you need.
Yeah, okay. I need to find.
Yeah, good.
Well.